Good morning, everyone. Thanks for coming. My name's Al Karlin, and I'm with Dewberry now. We'd like to thank Scott and Shrug, Scott Weissman and Shrug, for giving us this opportunity to talk to you all today. Just by way of brief introduction, if you don't know me, my name is Al Karlin. I came from the University of Arkansas, where I was tenured in 3 departments. Spent a short time on the private side, and then about 2004, 2005, I started with the Southwest Florida Water Management District. I finally retired about 1.5 years ago, and now I'm kind of part-time with Dewberry. I'm accompanied today, kind of virtually, by two folks, other folks at Dewberry, and I call them unindicted co-conspirators because they were kind of drug into this this whole thing. Josh Novak is with our Denver office. He's our technology manager, and Ray Miller is our NHD production manager, as well as a project manager here in our Tampa office. I kind of gave this as a abbreviated presentation last week for the American Water Resources Association. And we call this presentation the updating of the National Hydrography Dataset to elevation-derived hydrology. This is an evolutionary approach, and I think through the webinar, you'll see why I call this an evolutionary approach. Just kind of as an aside, Scott and I were emailing last week, and I was thinking this was a 20-minute presentation. And when Scott told me, no, it's a 45-minute presentation, I said, don't worry, I can always pad it. And us professors, we can talk about almost anything for 45 minutes. So I'll try to keep this to the time period, and maybe we can have some questions and answers at the end. Just a quick topic outline. Today I'm going to be discussing some background for NHD, the National Hydrography Dataset, and then we'll talk about a little kind of information about what can we do with digital elevation models. How do you find the top of the hill? How do you find the bottom of the hill? Which is really a lot more difficult. And then get into what evolved for us from a D8 type feature extraction through Daemon, through the infinity approach, to using terrain indicators, planned curvature, and geomorphons. And then finally to where we are right now and how we find those blue lines that are make up the NHD. And lastly, I'm going to talk about just some ideas for where to go next. And on the right, you can see kind of our spirit animals, and in the spirit of everything here and in the spirit of COVID-19, we're all following best practices for CDC. Well, by now, now being 2021, most of us are very accustomed to working with, or at least seeing, LiDAR data. Here at Dewberry, of course, as most of the folks at the Shrug know, Dewberry has been heavily involved in acquiring and calibrating, filtering, and constructing LiDAR-derived products, DEMs, contours, and other features for a wide variety of terrain types. And, in Leon County, we obviously see various terrain types, including the 7 hills, as it were. Here at Dewberry, we mine multiple returns because we know LiDAR can produce more than one return for us to help interpret and create digital surface models, those first returns, and digital terrain models, the last returns, which are the things that we generally use for H&H modeling and things like that. LiDAR DEMs, those digital terrain models, actually constitute the heart and the soul of the USGS 3D elevation program, the 3DEP, here in the continental US. And again, most of us are familiar with the QL2 specification, being the USGS standard, 2 points per square meter, with a non-vegetated vertical accuracy of plus or minus 0.6 of a foot. And of course, in Leon County, we know we have a very high quality QL1 LiDAR data with a higher pulse density and vegetated or non-vegetated vertical accuracy down in the 0.3 of a foot range. So I think it is kind of important that we understand and remember those numbers, because what I'm going to talk about in a few minutes is a great deal different. So we, again, as a community, and now I'm talking about, all of us GISers and H&H modelers and engineers, have come to understand some of the advantages and limitations of infrared LiDAR data. We know that it doesn't see through water, and we know that there are some types of vegetation and land covers that are particularly challenging for using terrestrial LiDAR. But again, in general, we're all familiar with the LiDAR technology. Now, while we're all pretty familiar with LiDAR derived terrains, in general, again, as a community, we're not quite as familiar with interferometric synthetic aperture radar. We typically call this INSAR or IFSAR, if you like the USGS way of thinking. Well, IFSAR synthetic aperture radar is a ranging technology like LiDAR. It is also fundamentally different. Yet in both cases, the bottom line is that we try to identify ground and derived terrain. IFSAR, synthetic aperture radar, was collected to the USGS quality level 5 specification. Now, again, like I said, as a community, we're not as comfortable or familiar with this, but USGS QL5 is one pulse, one return, 1 point every 5 square meters. Remembering that in Leon County, we have somewhere between 12 and 18 pulses per square meter. Now we're talking about 1 pulse per 5 square meters with a non-vertical, a non-vegetated vertical accuracy of 1.6 meters, not 0.6 feet, not 0.3 feet, but 1.6 meter non-vegetated vertical accuracy. That's QL5, and that's the standard that was adopted for mapping Alaska. And Dewberry, along with its partners, Intermap and Fugro, mapped all of Alaska. It took 10 years to fly and map Alaska between 2010 and 2019. Those 5-meter cell-sized DTMs and DSMs are all available on the national map for download if you want to see some. And I'm going to show you a couple in a little bit. So one of the tricks, and it's really a trick, is to extract terrain morphology from either LiDAR or IFSAR point data, or a derived gridded product such as that DTM that we're all familiar with. Well, let me tell you, there's a lot of theoretical mathematics involved in converting LiDAR points or IFSAR echoes into a surface. Without going into a whole lot of detail on mathematics, just so that everybody has some kind of a bit of a theoretical background, the surface is actually described by a Morse function where height is a function of the horizontal position, and that horizontal position is known at a finite set of points. That can be visualized and expressed as either a regular square grid, which is what most of us, again, are familiar with, that digital elevation model, that DEM, DTM, or DSM, or as a triangular irregular network, a TIN. And like I said, most of us are more familiar with working with grid surfaces than TIN surfaces. And in the ESRI world, we have a whole host of tools that are available for working with gridded surfaces. Now, the terrain morphology that we derive from the LiDAR and the underlying geology produce drainage patterns on the surface. So it's the interaction of terrain morphology and the geology, what's the rocks underneath, that produce these drainage patterns. Again, without going into a whole lot of hydrogeology, in Alaska, where we'll be focusing today, and coincidentally as well as Florida, we're concerned with 2 or 3 generalized drainage patterns. They're either the dendritic pattern that you can see on the chart on the right, or a deranged pattern, again, the chart on the right. The third one is actually a radial pattern, and radial patterns are typical of volcanoes and mountains, which there are plenty of in Alaska. Really hard to find a mountain or a volcano in Florida, but actually the inverse is true. We've got plenty of sinkholes, and sinkholes tend to produce the same sort of drainage patterns here in our karst geography in Florida. So again, without too much history and detail, everybody probably knows that the USGS started constructing the National Hydrography Dataset, and the NRCS constructed the Watershed Boundary Dataset to delineate the surface water features, those water bodies and waterways of the US and natural watersheds. Here in the US, we're really fortunate because we are one of the few nations in the world that has a detailed inventory of our waterways and water bodies. The datasets originated in the late 1990s, early 2000s, from field survey and USGS contour maps that were digitized. And over time, over the about a 10-year period, they evolved to become uncoupled from those elevation maps and were updated and constructed from orthorectified imagery by state data stewards. So although the original concept was to keep the NHD and the WBDs, so Watershed Boundary Dataset, in line with the elevation data, as we developed more and less expensive orthoimagery, they kind of became uncoupled. Now, the hydrological units are coded in a nested or hierarchical set of values representing spatial and hydrological extents. It's numerically coded. HUC2's hydrological unit codes at the hydrological units at the 2 level are called regions, and these are the largest units on the map, as you can see over on the right. Each HUC2 is divided into multiple HUC4s, so we just kind of add another 2 digits to it to become subregions or basins, and then we take the HUC4s, add 4 more numbers, they become HUC8s, again subdividing smaller and smaller units into subbasins down to HUC12s, subwatersheds, and into local watersheds, HUC14s. So it's a kind of hierarchical system, and I'll show you a little bit more about that in a minute. With the USGS 3D elevation program and the incorporation of the Watershed Boundary Dataset into the USGS about 2 or 3 years ago, there's been a new emphasis on using all of this phenomenal 3D elevation program LIDAR and that 10 years worth of IFSAR in Alaska to update the hydrography so that it'll come back into register with the elevation data and to conflate the lines and water bodies to those elevations. So we have a true elevation-derived hydrography that is no longer a 2D data set, but a 3D data set. So as I indicated, we're going to focus on work that Dewberry's been doing to update the Alaska NHD to elevation-derived hydrography. So how are Florida and Alaska similar? Why would anyone in Florida even be interested? Well, certainly, Alaska and Florida are not comparable in size. Alaska is about 10, maybe 11 times bigger. Population, Florida has, you can see, almost 2 orders of magnitude more people. Coastline, you can see that Alaska has an enormous coastline, even though Florida has like one of the largest coastlines in the lower 48. We can see it's absolutely no match for the amount of coastline that Alaska has. And even though, today happens to be a relatively cool day here in Tampa where I'm situated, it's like 72 degrees outside right now. Our average temperatures don't come anywhere near those of Alaska, from -60 to, or -30 rather, to 60 degrees. The Alaska average high is just a little bit higher than the average low temperature in Florida. However, the drainage patterns are actually pretty similar. Here in Florida, we have a couple of major river systems, just like Alaska, which produce dendritic patterns. We have a lot, and this is one of the things that I worked on for 10 years at the Southwest Florida Water Management District, is that we have a lot of areas of deranged terrain where the flow is non-channelized. You've got catchments that collect water, and as the water builds up in the catchment after a good rain, it just overflows into another catchment. So there's no real channel that the water flows in. And then finally, like I said, we share in a rather strange way radial drainage patterns of mountains and volcanoes in Alaska and sinkholes here in Florida. And that's because of the geomorphology. Here in Florida, I think everybody is familiar that for the most part, we're sitting on a limestone, and it's karst as the water hollows out places in the limestone. We get this karst geography or geology. In Alaska, of course, there's very, very little limestone, but a phenomenon called thermokarst, where the freezing and thawing, alternating freezing and thawing, produces the same type of geomorphology, holes on the ground that as they thaw, collapse to form these radial patterns and these huge thermokarst lakes. And then, of course, in terms of land cover, the area that we're working on right now, it's called the North Slope, and one would think it's like a mountain, but it actually isn't. The North Slope is a very, very, very gently sloping area on the northern portion of Alaska that goes into the Bering Sea. Again, much like Florida, the elevation differences are very, very small. We're talking, like 50 meters of elevation over hundreds of miles. So the elevation is very, very gently sloping, resulting in swamps and marshes, bogs, much like the land covers that we see in Florida. So although on the outside, Alaska would seem to be like the antithesis of Florida, and it's about as far away as you can get from Florida, short of Hawaii, there are actually some very marked similarities. So some of the lessons that we can learn from Florida can easily be translated to here in Florida. So with that as a kind of theoretical background and a little bit of justification for even talking to this group about Alaska, today I'm going to focus on one of the projects that Dewberry was tasked to do from the USGS, one of the Alaska NHD projects. Here, what we're looking at is a subbasin, a Huck 8, that's called Upper Kubik River. And again, much like the Hillsborough River, the Kubik River runs, in this case, from the eastern portion of the basin to the west. The red lines represent Huck 10s, And Dewberry was assigned the 6 Huck 10s that you see in pink. These are watersheds. These were assigned to Dewberry to construct elevation-derived hydrography, to update it. The other Huck 10s were assigned to other consultants. And just for reference, because I didn't put a scale here, the area in pink that Dewberry was assigned, the 6 Huck 10s, is approximately, it's actually a little bit more than 2,000 square miles, which is about the same size as Polk County, Florida. So we're not looking at a small area. Like I said, it's about 2,000 square miles, about the same size as Polk County, Florida. So I'm going to focus in on one Huck 10, and this one's called Beaver Creek. And within Beaver Creek, we delineated we delineated multiple Huck 12s, and you can see them here in yellow. So these are sub-watersheds within the watershed of Beaver Creek. And we're actually going to focus in on only one of those. Zooming in even further to a single Huck 12, it's still in yellow. Today I'm going to focus on the Angayachum Mountains, and that's this Huck 12 that you can see here on your screen. Here we see the existing blue lines. These are the blue lines that are in the NHD right now that you can download from the US national map, and the watershed boundary, the yellow dashed line, over a hill-shaded digital terrain model. And the digital terrain model, of course, is derived from the IFSAR data that was collected, that 10-year data, QL5. This is our starting point to develop elevation-derived hydrography from IFSAR. So now the question becomes how to update that NHD WBD layer to the high resolution, and 5 meters, believe me, is high resolution for this area, terrain models. So to realign the NHD watershed boundaries with the elevation, we need to be able to find the ridges, as you can see here, that delineate catchments, the spill points, the lowest points along those ridges, and the path that water would follow to that lowest point along the ridge in each catchment, the red dot, if you will. Now, given pretty much any digital elevation, no matter how much random elevation changes there are in it, because there's always going to be noise in an elevation model, the top of the hill, the ridge boundary, is mathematically fairly easy to find and vectorize. So that kind of brownish line that you can visually see along delineating the basin, the bowl there, that line is actually mathematically pretty easy to find. There's no real problem there. Finding the bottom of the hill is a little more difficult than finding the top of the hill. And that's because given any elevation model, whether it's LiDAR derived or IFSAR derived, there's random variation. There's random elevation issues, noise that's introduced into the DEM when we create it. So a sink, a cell from which water cannot escape, may form anywhere along the surface, giving the mathematical illusion, and you can see that on the left-hand side, of the bottom of a hill. So to remedy this, and we heard in a couple of other talks today, the DEM's got to be preconditioned, and we fill the sinks, and there's lots of different ways to fill the sinks. But first, you have to find them. So the first issue becomes how to precondition, find the sinks and fill the sinks in the DEM, given the terrain type, and then to determine which depressions are real and which aren't. And this becomes particularly difficult in deranged terrains like the ones that we have here in Florida. So, like I said, finding the bottom of the hill and the route that water takes to get there is a lot trickier than finding the top of the hill. In the ESRI world of spatial analyst or 3D analyst and the ArcHydro tools were developed based on 2002 technology to fill sinks. which is a whole other topic, in the digital elevation model. So for simplicity, the approach to determine what to fill is based on zonal statistics and a standard statistical delta Z limit. Again, today's not the day that I'm going to go into a heavy mathematical discussion, but know that ESRI has figured out a way using their kinds of tools and good statistical background to find sinks. The same method can identify and knock down spikes, and that's what I'm kind of showing you here in the two slides. Well, following the fill step and the ESRI workflow, we use what's called a D8 method to determine a flow accumulation and a flow direction surface raster. So we're going to use this filled DEM to construct two additional rasters, a flow accumulation and a flow direction surface. And then from that, we're going to extract flow paths. And I like to call these things flow lines because they may or may not be streams. It's just a potential way that water could flow along the flow direction raster surface. So the general approach in the ESRI world is basically a kind of six-step model, and we can easily model this in Model Builder, and that's what we've done, of course. We can construct an ESRI model builder using the Spatial Analyst ArcHydro tools. And like I say, it's kind of a six-step process. In the case of Alaska and our IFSAR DTMs, steps 1 and 2 have actually been performed by the USGS on the data, and those are the data that are available out on the national map. So the actual processing starts with filling sinks, computing that flow accumulation, flow direction, and stream rasters, and then vectorizing the stream raster. Now, I have omitted a lot of detail because you can see there's more than those simple steps here. But given that background and what we now know about terrains, what I'd like to do is just peek under the hood a bit and see what ESRI is doing, or maybe what they're not doing in whatever case. The general mathematical approach that ESRI uses is one of the Raindrop models. And the particular variant on it is called a D8. And the D8 model, as you can see, passes a 3x3 kernel of cells. So each in A, each one of those cells represents a 5 meter by 5 meter pixel on our DEM that's been conditioned. It passes this kernel over the raster to determine a single flow direction from one cell to the next lowest cell, and it encodes it with a 1, 2, 3, 4, or 1, 2, 8, 16, 32, 64, 128, or a 255 if it happens to be the middle cell and it's a sink. If the Raindrop model can't determine the next adjacent lowest cell, well, it keeps going, keeps searching outward. It'll go to the next ring and the next ring and the next ring until it actually finds the next lowest cell. This process may result in long straight flow lines in areas of very low relief. And remember now, I'm dealing with a DTM that has a 1.6 meter, I'll say that again, 1.6 meter non-vegetated vertical accuracy, and in vegetated areas, of which there are a lot of in Alaska, just like in Florida, there's no telling what the vertical accuracy is. So we have cells that could be the same for very, very long distances. This process also results, like I say, in those low flow lines, but also the technique tends to result in feathering, lots of little flow lines that in upper reaches of creeks or even along the flow lines themselves in some cases. In spite of these gotchas, the D8 model produces a monotonic path that's really easy to vectorize. If you think of it, it's just going from one cell to the next cell to the next cell, and it produces a very easily vectorized stream grid. The ESRI D8 model approach, when processed against a preconditioned DEM, like I said, should trace monotonically downhill from the spill points to the sinks of each catchment. Consequently, the flow lines from cell to cell can be easily vectorized to produce an elevation-derived flow line. And each flow line conforms faithfully to the underlying DEM. Of course, this assumes the correctness of the underlying DEM. So coming back to the Engagement Mountains and this particular subwater watershed, and a cell accumulation of about 12 acres, about 50,000 square meters of Alaska, and a no-fill DEM. So I didn't fill the DEM. We see significantly more flow lines. So here's where our starting point was. These are the USGS currently NHD blue lines. And here's what we get. Significantly more flow lines as compared to the blue lines, but you also see a lot of discontinuities in the flow lines. Filling the DEM using ESRI fill routines. Next, what I did was I filled all of the depressions that were 2 acres or less, and you should have been able to see that actually fills in a lot of the places. But there are still a couple of areas of discontinuity, and the yellow watershed boundary lines, that dashed line, are the current watershed boundaries in the NHD, and you'll notice that there are numerous places where the flow lines cross watershed boundaries. I'll kind of address that a little bit later. So, are there alternative approaches? Are there alternatives to the ESRI approach to finding these flow lines? And of course there are. Outside of the in the non-ESRI raster-based world of OSGeo, the OSGS GRASS saga group, there are other approaches to filling the DEM. The TerraFlow approach is designed to identify sinks in areas of low slope, terrain morphology again, the slope being an indicator of terrain morphology, while the AT, which we sometimes call the A-star approach, and the impact reduction approach minimize the impact of high and low, both types of pits and spikes in the DEM. There are a host of other smoothing approaches. Perona maloconvolution is one approach that ESRI takes. You can find that in the ArcHydro toolbox now. Gaussian smoothing, and a median, mean, lots of other types of smoothing approaches exist. So the short answer is, are there approaches other than the D8 ESRI approach to solving this problem? And the answer is yes. So the first approach that we looked at to as an alternative to the D8 is called the Digital Elevation Model Network approach, DEMON for short, and kind of cute. This is a different approach. It's not a raindrop approach. This is a sheet ribbon flow approach that constructs planes along the edges of each raster cell and directs flow along those planes. The flow is no longer restricted to 8 directions, but an infinite number of directions that are encoded as angles, again, starting in the east and going clockwise. To be real honest, we passed on this approach. We found a couple of issues with it and just kind of passed on this approach and went directly to what's called a D-infinity approach for modeling flow in those very low relief areas. The D-infinity algorithm is actually derived from that DEMON approach. And again, this is kind of our evolving approach to the problem. This model, the D-infinity model, makes some improvements to the DEMON model by eliminating spurious flow directions, by using only 3 corners of the cells to make triangular faces. And this approach was proposed first by Dave Tarberton. You might know Dave, in 1997. We found that although the flow was really better delineated by applying the D8 infinity algorithms. This necessitated constructing very small multiple patchworks of rasters. And we encountered difficulty determining the best vector representation of the flow line rasters. ESRI actually does not have a way to determine the flow path through a D-infinity network. And here we see the results of a D-infinity network as multiple flow paths. And you can see this big, thick area. ESRI really doesn't provide us a way to determine the best flow path through that. Bottom line is you end up with the same sort of issue from several machine learning probabilistic approaches that we tried, and it's just really troublesome. So just kind of in a nutshell, you can see which flow path is it that goes through one of these D-infinity modeled areas. So the D-infinity model requires additional preconditioning, and the more preconditioning you do, the more time it takes, and is it really worth it? It captures complicated braided channels, but you still need to determine where the flow path is. And there's no real good way to do that in the ESRI world. So we moved to another model. We moved to looking at this model, this Geomorphon model, which is a much more recent model. You can see it's a 2013 approach to recognizing patterns in landforms. It's kind of based on D8, but it's a lot different. The idea here is that each cell is coded with an octet of either ones, negative ones, or zeros, depending on adjacent cells to it. If the cell adjacent to it is higher, it's coded with a positive one. If the adjacent cell is equal to its elevation, it's coded with a 0. If it's lower, it's coded with a negative 1. So each cell gets 8 in octet values, each value being either a negative 1, a 0, or 1, depending on its neighboring cells. Well, if you do the mathematics, of course, that's like 3 to the 8th different combinations, 161 different possibilities, of which only about 500 are really meaningful in the terrain. And of those 500, only about 10 actually mean anything that would be real to us. Now, the Geomorphon coding is computed. It's really pretty fast. And right now, there are routines in GRASS, QGIS, and Saga to compute geomorphons, and you can do it through ArcPy in the ESRI world. The Geomorphon model is sensitive to how far out you're looking. So I want to kind of get to the heart of this. The Geomorphon model is very sensitive to your field of view. The further out you look, the coarser it gets. So what we ended up doing was computing the geomorphons at a 5-cell field of view, a 10-cell field of view, and a 15-cell field of view. And I want to just show this to you very quickly. So here's back to our Engagement Mountains. Here's our geomorphons at a 5-cell field of view, and you can start to see the flow lines, those darker areas, in blue against the yellow background of the geomorphon slopes. At 10-cell field of view, it becomes a little bit better defined, and we can see the flow lines pretty well there. And here's our flow lines overlaid onto those geomorphons. You can see there's a pretty good agreement, except we still get these long straight areas. And you know, we're obviously looking at straight areas here that are in the range of several hundreds of feet. So not very desirable. When we go out to the 15 cell look field of view, we see just big flat areas, which are really uninformative. So I'm going to zoom back in to that 10 cell field of view, and you can see that the flow lines are really pretty well following the valleys, the blue areas, but there are those areas of discontinuity even in the geomorphons. The geomorphons have advantages and disadvantages, and I'm kind of just going to blow over Lake Manacocosa, and you can see that the lake actually shows valleys, which is kind of bizarre, but that's just because of the field of view. If you're sitting in the middle of the lake and you're looking out toward the edge, of course you're going to see a valley. So the geomorphons have a bit of a issue with them too. So we finally ended up looking at a combination of the geomorphon along with A-star cost surface. So I'm going to show you where we ended up in our evolution as I've been doing this from the very beginning. Here we're looking at the existing NHD blue lines. Here's what we get when we use our combination of the geomorphons, the A-star cost surfacing, and some other morphological indicators. We get a very, very dense network. This was extracted with a 3-acre accumulation. We extract again at a 12-acre accumulation, and you can see we're now getting nice continuous flow lines that are more dense, more information than the existing NHD. And when we combine the additional density from the 3-acre flow accumulation with the 12-acre flow accumulation, we get our final product, meeting the density and expectation requirements for enhanced elevation-derived hydrography. Last thing, of course, is solving the problem of the watershed boundaries. And basically to do that, we take the existing flow lines, do a reverse network tracing, and update the watershed boundary data. So I'll just show you again, looking in a very small portion of the Engaged Mountains. We're looking at catchments. I like to call them accumulation areas rather than catchments that were derived here at the 12-acre size. You can see our flow lines, and now our watershed boundaries are obeying the catchment boundaries, those accumulation areas. So here's looking at the difference between the existing non-elevation derived watershed boundaries and the elevation derived watershed boundaries. To getting there is a whole different argument, whole different discussion, something for a different day. So just a couple of final thoughts. Are we there yet? I don't think so. I think we still have a long ways to go to get this process automated. We're working closely with Dan Dozic and the ArcHydro team at ESRI to update some of the ESRI tools to construct new workflows that will help us delineate more efficiently, minimize manual cleanup, do additional vector smoothing, and integrate some AI technology, machine learning technologies into the process. So the bottom line is, has the evolution gotten us there yet? And I don't think so. So just a couple of quick acknowledgements. The work in Alaska, of course, was done for the USGS. We have had multiple meetings with the folks at the USGS in the Alaska NHD program and Alaska Fish and Wildlife. And I've got to tell you, Dan Dojik and ESRI and I spend many hours on the phone bouncing ideas off of each other to make this process better. So I appreciate their patience. Last thing, and I see I'm at 45 minutes. Scott, exactly as I said I would be. I thank you for your attention, and if there are any questions, I'll be happy to try to answer them. Here's our smiling faces, not our spirit animals, and some contact information. And with that, Scott, I'll give it back to you.
Okay, any questions?
I know I went over a lot of detail, and
Yeah.
believe it or not, that's just scratching the surface.
I'm not seeing any questions coming across. Could somebody just enter in and let us know that the question dialogue is working?
Yeah, I know I can't see anything either.
Let me see. Yes, we got a comment. So great presentation.
Okay, thank you.
Got 2 thumbs up.
And one of the things that I would like this group to think about is maybe encouraging. Right now, the Florida Department of Environmental Protection, DEP, is the state data steward for our NHD. And for a very long time, I worked with Dave Anderson, Joe North, previously with DEP to update portions of Southwest Florida Water Management District's NHD. And we went like Huck 8 by Huck 8 through the district. At the time, we were updating it to the district's imagery, the ortho imagery, and of course, that's a 2D process. And there, of course, you really can't expect the ortho imagery, which can now be very precise, to match the elevation, the LiDAR, which at the time was a QL3 type LiDAR. So I would encourage, Shrug and Leon County to think about running a pilot project using the QL1 data and the high resolution imagery, the 3 and the 6 inch imagery that we have for Leon County to pilot out an NHD project to update, maybe one or two Huck 10s in Leon County. The processing, like I say, it's going to be an evolving process. And of course, Leon County has a tremendous amount of infrastructure and data that can augment and enhance the NHD processing. So I think that would be, a great project to think about.
Okay, we got a question from Param Maharaj. Are you focusing primarily on capturing the flow line network, or plan to work with water bodies as well?
Yeah, good question. Or it's kind of cliche now to say it's a good question, but yes, we are actually working again with ESRI very closely. If you're familiar with the wetland identification model that is part and parcel now of ArcHydro, we're developing that along with some AI technology to extract water bodies. And the USGS specification for a water body is 2 acres, 2 acre minimum. And for a lot of H&H modeling, particularly in the district that I worked with, Southwest Florida, our water bodies were down at half an acre. So yes, we are working. That's again a whole other discussion. We are using and developing AI technologies to find water bodies that are, again, going to be incorporated into the NHD. So yeah, I was concentrating today on flow lines, but we're using similar AI technologies to augment the water bodies. Thanks for the question. And that's something that, you know, if you're interested, Josh has been heading up that particular effort here in Dewberry. I'm more of a flow line guy. Josh is more of the water body type.
Okay. Not seeing any more questions, so I guess we'll conclude this session.
Well, thanks very much. Again, thank you for the opportunity.
You're welcome.